All right, so we're going to talk about the life cycle of a star. And we'll talk about big stars and small stars and how their life cycles are different. So the first thing I want to talk about is how all stars start their life. All stars start as a nebula, and the nebula comes from a supernova, from a previous star, and it explodes, and when it explodes. When it does that, it sends all of its material out to the far edges of space. Well, not the far edges of space, but a ways from where it started. And you end up getting a bunch of little pieces of dust and gas. And we talked about the snowball effect when we were making the plan, or when we were talking about the planets. So that snowball effect then kind of starts to take place, and it gets closer and closer together. And this is the Horsehead Nebula. So this is a close-up of what the Horsehead Nebula, or the actual Horsehead part of the Horsehead Nebula, looks like. This is 3.5 light years across. So it takes 3.5 years for light to go from over here to over there. So it's a little bit on the big side. Then you get a protostar. So a protostar is the beginnings of a star, when everything in the center is starting to get really, really warm, and you can't see it with your eyes, but you can with infrared. So with infrared, you can see these warm areas in the sky, showing that there's a protostar forming. After the center of the protostar gets to be 27 million degrees Fahrenheit, not exactly cool, so 27 million degrees Fahrenheit, hydrogen starts burning into helium. So you take 4 hydrogens, and those 4 hydrogens come out and they end up making a helium atom. And when that happens, a lot of energy is released. And when that energy is released, you see the sun shine. So that's what makes the sun shine. And that is when a star becomes a main sequence star. So a main sequence star is where stars live most of their lifetime, and they can be any size, they can be any brightness. So supergiant stars can be main sequence stars, and teeny tiny red dwarfs can be main sequence stars. The larger stars actually live the shortest lives because they have more stuff. It's burning a lot faster because it's so much hotter, so it burns through it a lot faster, where the little stars, they don't have very much material, but they're not hot enough to burn very quickly. So large stars live for a very short time, and small stars live for a very long time. So this is just an example of some main sequence stars. This is a blue giant, and this is a yellow dwarf, which is our sun. This shows you Jupiter, which is a brown dwarf, which you'll learn about when you do your lab. The brown dwarf is something that is a star that wasn't able to actually ignite in nuclear fusion. So they consider Jupiter a possible brown dwarf. Usually they're a little bit bigger than Jupiter, but they do think that Jupiter may be a brown dwarf. So how long a star lives and how it dies depends on how much stuff it starts with. So if you have a lot of stuff, so 3.5 light years of stuff, and let's say that formed one star, which it wouldn't form a bunch of stars, but let's say it did form one star, that'd be a really, really, really big star. And it wouldn't live very long, but it would have its own life cycle. So it would be a protostar, a blue supergiant, and then it'd turn into a supernova when it died. This is our sun right here. So we start out as a protostar, and then you have a star that's like ours. It then turns into a red giant, and then it has a planetary nebula. It's also called a nova explosion. It's not special enough to actually have a supernova, but it does get a nova explosion, and then you end up getting a white dwarf. So that's how our star will die. So this is the life cycle of a medium or dwarf size star. So we just talked about it, but I want to show you some pictures. I would always consider, I look at this picture, I love this picture, and you'll see it again in your lab. When you're in a nebula, it's like being a fetus, and then the main sequence is going from being, born to being my age, kind of middle age, or not quite middle age yet, even though I am, but we'll pretend I'm not. And then your middle age, that's when you turn into a red giant or a red supergiant. So that's when you're going to die before too long. You have quite a bit of time left, and then you have old age and death, and that's when you have a white dwarf or a black hole. This is Arcturus. Arcturus is a red giant, and it shows you how much bigger a red giant is from our sun by taking a look at that picture. When you have a sun-sized star, this is more what a nova explosion looks like. So you've seen pictures of supernova explosions, which are huge. I mean, they're monstrous, and we'll look at some of those in a second. But this is what a nova explosion looks like. So it's not quite as big. It's also called a planetary nebula. And then after that explosion, the sun is going to shrink into a star that's the same size as the Earth. So it's very, very small. And at that point, it's going to start fusing helium into carbon. So it goes from burning hydrogen into helium to helium into carbon. So this is a white dwarf. They're actually relatively dim, but so you can see it's very, very white. Okay, so let's talk about a massive star and how it lives and dies. This is Betelgeuse or Betelgeuse, depending on who you are or where you hear it. It's 430 light years away, and this is a red giant. So Betelgeuse is a very big red giant, and like I said, 430 light years away. So after it's a main sequence star, it turns into a red giant, or when it's a red giant star to start with, it's going to turn into a red supergiant. Then you have the death of a massive star. So this is a supernova explosion. You can see it explodes its material much farther out, and that usually happens when the star is 3 times greater than our sun. And notice I say implosion. I think you'll read about that in a second. What really happens is the star implodes on itself and then ejects all the material. This is the biggest supernova ever recorded. So this is 240 million light years away, which means the light from it coming towards us 240 million years ago. But it is the biggest supernova that's ever been seen or recorded, and it's an absolutely beautiful, beautiful sight. And then black holes, you can't really see them. They're the end of the life cycle of a massive star, and not all of them, but some. If it's a really, really, really big star, it'll actually become a black hole. And you can't see the black hole itself, but you can see the matter around the center. That matter around the center that's what's being shredded into teeny tiny little pieces, which releases a lot of energy. So it releases a lot of X-rays, and then that spews north and south, or not necessarily north and south, but it spews jets on either side of the black hole. And so that's how we were able to detect black holes. We knew something had to be powerful enough to be able to destroy all this material. And so we know that there's something there that's super powerful, and the black hole is super, super dense. It's super, super small, but it has a huge mass. So that huge mass actually causes it to have a ton of gravity and break things into pieces. This is what they think the center of a black hole might look like. This is the hypothesized center of a black hole, but again, we don't know because we've never been there. Now, neutron stars are what you get if the star isn't quite big enough to form a black hole. So it has to be super big, like 20 times, or well, at least 3 times the size of, to be a black hole, it has to be at least 10 times the size as the sun. So it has to be really, really big. So if it's not that big, you're going to get a neutron star. And a neutron star, this is what they look like. You can't really see it very well here, but you can see the X-ray image really, really well. So neutron stars are these really, really small, dense stars. They're like 7 miles across, and they are super, super dense. If you have a teaspoon of it, it would weigh the same amount as the Earth. So it's super dense, and that is what you would get if it starts spinning. You get a pulsar. So this is a neutron star. So massive stars, like I said, 3 to 20 times the size of the sun. They can be 7 to 18 miles across, and the density is twice that of the sun, but it's 1,000,000 times fainter. So I love this picture. This is showing the neutron star across Vancouver. As you can see, it's covering quite a bit. So if that neutron star were to come into Earth like this, aside from us being completely killed, this is the size it would be. And this is a pulsar. So a pulsar is a neutron star that's spinning really, really fast. And radio telescopes pick up the sound, and let's see if this will play for us. No, it's not going to play for us. Darn it. You can actually hear the sound of a pulsar, and they click, and they go around really, really, really fast. Sometimes as much as 3,000 times per second. That's how fast they can go. So let's talk about the life cycle of a star. Everything starts as a nebula, and then it becomes a protostar. That's when it starts nuclear fusion. Then you either have a medium or dwarf-sized star, and that's on its main sequence. Then it starts as a red giant, right? Or then it swells into a red giant when it starts to die. It then has a nova explosion, or just a planetary nebula explosion. It then goes down into a white dwarf, and over a period of time that white dwarf will turn into a black dwarf. If it's a massive star, it'll start as a giant star, so it's a giant main sequence star, and then that turns into a red supergiant, so it's even bigger. Then you have your supernova, so the supernova explodes. And if it's 3 to 20 times the size of our star, you'll get a neutron star, and that neutron star can become a pulsar. But if it's bigger than 20 times the size of our star, you'll get a black hole. So that is the life cycle of a star, and hopefully that's it. If you have any questions, let me know. Also, the videos are going to help you quite a bit. They go through it very well too. So that should be it. Let me know if you need anything.